I've got the power! If you want to have the power, wow, throw away this marker, first of all. Good. If you want to study power, you're probably going to remember that it's work divided by time. And of course, work is change in potential energy, because you're going to be converting potential into kinetic, or kinetic into potential, or something like that. Or maybe, I don't know, potential into heat. Heck. But I want to remind you that we defined electric potential by saying that it was change in energy divided by charge. And this is sort of the same thing, I'll put this in quotes, as change in potential energy divided by some charge that's passed through some area. So I suppose that's pretty reasonable. I'm going to take this over here, solve it for delta U, and say that it's voltage times change in charge. I'm going to plug it into this equation over here. Watch me. Seriously, just watch me. I'm going to plug this in and I get voltage times change in charge divided by change in time, which is, well, let's do a little bit of rearranging. But you see here, delta Q over delta T. Delta Q over delta T is something awesome, and I'm going to multiply it by voltage. So this says that power is current times voltage, and the units of power we know to be watts. So I guess I'm saying 1 watt is 1 amp times 1 volt. Ooh. Watts is amps times volts. Now this equation is such a beautiful equation, it is valid for all electrical circuits. But we could take this equation 2 different directions using Ohm's law, and this would not be the case. Let's see, I should box this in here. This is valid for all electrical circuits. But I'm going to take this equation and use V is I R in one direction, and I'm also going to use I is V over R in the other direction, and get myself a couple different equations which will not be valid all the time. In fact, they'll only be valid in an ohmic material. This is Ohm's law, and in an ohmic material, you want to guess what defines an ohmic material? Yeah, it obeys Ohm's law. So only in the case of a simple resistor will we be able to use these 2 equations that I'm deriving right now. First, I'll say that V is IR. That will get me I times IR. That says power is I times IR, where IR was V. So this is I square R, and this guy is named Joule heating. That's the name of this equation right here. And Joule heating is an excellent and powerful effect for a resistor. If you put more and more current through a resistor, then you get that resistor to transfer more and more energy into heat. So that's why the resistor heats up. In fact, any wire that you put a current through will heat up by Joule heating. And if I take the other equation, the I is V over R, I'm going to get power is V over R times V, which is simply V square over R. This one doesn't have a pleasant name, but do you remember, I want to point out to you the similarity in issue that we have here. These purple ones, are not always valid. They're only valid for an electrical circuit that obeys Ohm's law. And there are a lot of things that don't, and we'll study those things in great detail. But for those, these are not valid equations. But if I've got a system that obeys Ohm's law, a V is IR kind of system, then I'm going to be able to use this equation or either of those. Otherwise, I got to stick with this one. So I'm going to write down 3 equations for the energy stored in a capacitor. The energy stored in a capacitor is 1/2 CV squared, and of course the energy stored in a capacitor is 1/2, oh man, wasn't it Q times V? Oh yeah, but the energy stored in a capacitor, well, you know that is just Q squared over 2 times the capacitance of the capacitor. Sure, but look at the similarity between these 3 equations. Power is IV, power is I squared R, and power is V squared times, oh shoot. Look at this. Look at this. I'm doing this, and you're not even going to tell me that I screwed that up? It's V squared over R. What the heck is wrong with me? And you, by extension, because you didn't tell me. whatever. Maybe tell me in the comments. Tell me that you're embarrassed that I screwed up such a simple thing. So, of course, oh wow, there's a lot of similarity between these. Maybe I should have changed the order of those two. Whatever. But it starts with a simple equation and then is related by a second simple equation. This is the path between these guys is Q is CV, and the path between these guys is V is IR. Okay, cool. A lot of similarities, but my point with all of this nonsense is to say that you choose equation based on what's being held constant. In some instances, over here with this equation, you'll be holding the voltage constant and thinking about what happens to the power if you change current. I guess you'd want this equation then. But if you're holding the voltage constant and seeing what happens if you're changing resistance, then you look over here. But if you're changing resistance and holding current constant, then you're looking over here. And there are physical ways, there are systems that you can build that will hold either voltage or current constant. And so these equations are, well, you'll need to choose the correct one. And that's the same thing we talked about in class a great deal. If you're using one of these equations, you'd better know what both the variables are doing. Because if there's a variable doing something unpredictable, it can change your result. In fact, like the simplest example is, take a capacitor. If the capacitance gets smaller, what happens to the energy? Now, that depends, because if the capacitance gets smaller in this equation, then you'll have less energy, and if the capacitance gets smaller in this equation, then you'll have more energy. So this is the fundamental issue. You need to know, in this circumstance, whether voltage or charge is being held constant, and over here, if you're trying to figure out whether power goes up as resistance goes down, then or down as resistance goes down, you need to know whether current or voltage is being held constant. So there's an analogy between these guys, and I hope you have the chance to play with a lot of problems, because that's how you will become understanding of this sort of a system. There is a fantastic there's a fantastic system to measure a battery. So you get this AA battery, and when I was a kid, this system was all over the place on battery packs that came from Duracell primarily. And then there were these other guys who realized they could actually build it into the battery. So let me show the system here. The system is like this, and it's a well, it's a little strip of resistive material, and it connects to the battery. And it connects to the battery with a switch. When you want to connect it to the battery, then you can connect it to the battery. And this resistive material heats up when there's a sufficient current going through it. And when it heats up, there's probably a liquid crystal or something also that it goes clear to expose a yellow background. So it's got a meter on here, and it says bad and amazing. So the cool thing is it will heat up more quickly where the resistance is more. And you want to tell me if the strip is shaped like, well, like a wedge there, where would it heat up the fastest? Where is the greatest resistance in here? Sure, it's down here. So they're going to give you down here heating up really quickly. Even with a bad battery, down here will heat up, and you'll see red or yellow or however they design it. And then if the battery's even better, then there'll be even more current flowing through here. I guess the current flowing through there is related, let's see, we got V is IR, so I is V over R. And for a given, oh man, I guess there's some key current that's gonna cause this to heat up, man, by P is I squared times R, because we've got Ohm's law here, that the resistance is getting less and less up here. So for a current going through there to get enough power to heat up the sucker, we know that we're going to have sufficiently high resistance. So if the wow, we got another equation for power that we could use. We could say it's V squared over R. If we want big power, oh, but the voltage is changing throughout this thing. Wow, it's really complicated. So if we have a better battery, suffice it to say that there will be more current going through here because of this equation right here. The resistance of the entire thing is fixed, So there will be more current going through there if the battery is better. And if it's an amazing battery, then it's going to have so much current going through here that we can look at this equation and say, yeah, even when the resistance is very small, there'll be enough power to heat up that wire. And this is Joule heating in action. Pretty cool. One more thing I want to discuss is the idea of energy usage. I got an electric utility and they bill me in kilowatt hours. Kilowatts times hours. And it's a unit of energy just like any other, and it turns out it's convenient for them because they're measuring your usage in watts, and hours is a nice healthy time unit, a little bit more convenient for a household than a second would be. So let's figure out what it is. A kilowatt is 1,000 watts, and an hour is 3,600 seconds. And you know that a watt times a second is a joule, so we're talking about 3.6 million joules, which is sufficient energy to lift up 3.6 million apples, if they're small apples, or 3.6 mega apples. Yeah, 3.6 million apples by 1 meter. Wow. Now, the beautiful thing about electricity in the United States, especially in the central United States, is this amount of energy, the energy to lift 3.6 million joules, is that it will cost me a dime, 10 cents. Yep, cool. And this is why you can't get a bum from the street and tell them to come with you and pedal a bicycle all day and then pay them minimum wage. Yep, because they probably won't even be able to generate 1 kilowatt hour over the course of the day, especially if they're not in good physical shape. And you'll have to pay them many, many dollars, tens of dollars. Wow. And they've not even made you a tenth of a dollar. That's a great way to lose money, but maybe it'd be a great way to get bums in shape. Bye-bye.